Now that we're done with measure of center, we're going to introduce the measure of variability. The very first measure of variability is called the range of the data, which is the difference between the maximum value and minimum value in your collection. For example, two corporations each hire 10 interns. Starting salary in corporation A is given below: $41,000, $38,000, $39,000, and so on. To find the range of the data, find the minimum value, find the maximum value. The minimum value is 37, the maximum value is 47. If you do the subtraction between these two values, you see the range is $10,000. The simplest measure of variability, as we saw, is the range. But it doesn't take into account the rest of the values. It only takes the minimum value, the maximum value. So I expect you to ask, what happens to the remaining n-2 values in your collection? In that case, we're going to use standard deviation. Our primary measure of variability involves the deviations from the mean. So if the mean of the data is x bar, the deviations are x1 minus x bar, x sub 2 minus x bar, and you continue this process, xn minus x bar. That is, the deviations from the mean are obtained by subtracting the mean from each of the n sample observations. A deviation is positive if the observation is larger than the mean. Otherwise, it's going to be negative. And if it's equal to the mean, it's going to be 0. If all the deviations are small in magnitude, then all xi's are close to the mean and there is little variability. Finally, if some of the deviations are large in magnitude, then some of these observations or numbers x sub i's lie far away from the mean. It shows a larger variability in our data. You see more spread. A simple way to combine the deviations into a single quantity is to average them. But if you average them, you're going to get 0. Why is that? The summation of xi minus x bar can be written as, you can move the summation into parentheses, the summation of xi's minus the summation of x bar, which is basically the summation of xi's. You're just adding all of these observations together minus n times x bar. Why is that? These are the properties for the summation. When you're talking about the summation, I starts from 1 to n of x bar. X bar is a fixed value. You're basically saying that, hey, I'm just adding x bar by itself n times, which is n times x bar. So that's how you get n times x bar. Well, what's happening now? You have the summation of all observations minus, well, this can be written as n times the summation of xi's divided by n. This is the definition of x bar. Remember that. The average is the summation of all observations divided by the n, which is the number of values in your collection. Here you can cancel out n and n, and you get the summation of xi minus the summation of xi, which is basically 0. So the summation of deviations, if we don't do anything, is nothing but 0. So how do we remedy that? To remedy this, we're going to do a little bit of adjustments and algebra. To prevent negative and positive deviations from canceling out each other, what possibility is to use the absolute value? So if we calculate the average absolute deviation, this is the summation of absolute value of xi minus x bar. Because the absolute value operation leads to a number of theoretical difficulties considering raising them to the second power instead. So this is the best remedy that we came up with. x1 minus x bar to the second power. We take each deviation and raise them to the second power, then add these together. The average squared deviation, which is the summation of xi minus x bar to the second power divided by n, is going to be our formula that we're going to use. For several reasons, we divide the sum of squared deviations by n minus 1 rather n. This is specifically for a sample. For population, you're going to leave it as it is. But when it comes to sample, we're going to use n minus 1. The sample variance, which is denoted by a squared, is given by the summation of deviations to the second power divided by n minus 1, or s sub x and x divided by n minus 1. The sample standard deviation denoted by s, and it is square root of the variance. So standard deviation is the square root of the variance, everybody. It's best to obtain a squared from statistical software because eventually you end up with a lot of data in your collection. It helps you to calculate these with more accuracy as well. So if your calculator doesn't have this capability, you're going to use Python. In this class, we'll learn how to use Python as well to do the calculation very fast for us. So again, an alternative expression for the numerator of s squared is s sub x and x, which is equal to the summation of deviations to the second power, or as you remember, you can write it as the summation of xi's to the second power minus the summation of xi to the second divided by n. So what's the proof behind this formula? Remember how we defined x bar. X bar is the summation of all observations divided by n. If I multiply both sides by n x bar and raise it to the second power is equal to the summation of xi's to the second divided by n. So we are not doing anything special here. You're just multiplying both sides by n. Why is that? Because we are raising these to the second power. Take a look. Here you have x bar, which is equal to the summation of xi's divided by n. If I raise both sides to the second power, I have x bar to the second equals to the summation of xi's to the second divided by n squared. So instead of having n squared on the denominator, I'm going to multiply both sides by n and it get rid of n squared on the denominator. Now, the summation of xi minus x bar to the second is equal to the summation of xi to the second minus 2x bar times xi plus x bar to the second power. What is this? This is nothing but algebra. If you have a minus b to the second power, that is a squared minus 2ab plus b squared. But now here you have xi minus x bar to the second, which is xi squared minus 2xi x bar plus x bar to the second. Now what? Now this is equal to, you can basically find the summation of each of these terms separately. So the summation of xi to the second minus 2x bar, the summation of xi's, plus the summation of x bar to the second, which is nothing but the summation of xi to the second minus 2x bar. And remember the definition of the summation of xi, which can be written as nx bar plus, well, finally here, you don't have any I to work with. It's a fixed value. This is just the average raised to the second power. So if you find the summation of x bar to the second, you're basically adding x bar to the second n times. This is n x bar to the second. Well, this is equal to the summation of xi to the second minus n x bar to the second. Please note that here you have negative 2 x bar to the second times n plus n x bar to the second. If you combine these two together from algebra, this is negative n x bar to the second. Very good. So we just showed that the summation of xi minus x bar to the second can be written as the summation of xi to the second minus n x bar to the second, or you can simplify this and write it nicely as the formula, as you can see just right here. They are equivalent to each other.